In this example, we have a fuel that is a gas that contains a mixture of hydrogen, methane, ethane, butane, and isopentane. It's flowing to a furnace at a volumetric flow rate of 1450 meters cubed per hour, a temperature of 32 degrees C, and a pressure of 125 kilopascals gauge. We want to use the law of corresponding states to determine the molar flow rate of the fuel. So I'm going to do a couple of things. First is whenever I see things that are in these relative temperatures and pressures, pretty much the first thing I do is I take the time to convert these over to absolute. So for temperature, I'm going to add 273. This is 305 Kelvin. For pressure, I'm going to add 101 kilopascals, and so this is going to be 226 kilopascals absolute, or roughly 2.26 atmospheres. Okay, so what's my process here? In this particular case, I am given a volumetric flow rate. I want to find the molar flow rate. I'm going to do that using the law of corresponding states. So that says that V is going to be Z nRT over P. Now I have T and P. That's no problem. I guess I would rather solve this for N, right? V dot P over Z RT. The trick is to figure out what is Z. So in this particular case, I've got a mixture here, and I need to determine the critical temperature and pressure, right? So what is Z? I'm going to get that using the chart. I'm going to need TR and PR. In order to get TR and PR, I'm going to need TC prime and PC prime. And in order to get those, I'm going to need to know TC and PC of each of the individual substances. So let's go to the back and find the data we need. So we have H2CH4, C2H6, NC4H10, and IC5H12. TC is 33.3 Kelvin, 190.7, 305.4, 425.17, 461.00. All of those are in Kelvin. And PC is 12.8 atmospheres, 45.8, 48.2, 37.47, and 32.9. All of those are in atmospheres. Now, hydrogen, remember, is going to always require correction. I'm going to add 8 Kelvin. I'm going to add 8 atmospheres when I do the calculations. So the pseudocritical is going to be, well, I have 35% hydrogen, and the critical temperature is 33.3. And I'm going to add 8 to that. And then I have 25% methane. And 20% and 10% and 10% again, and I end up with TC is 211.827 kelvins. So that's the pseudo-critical temperature. I'm going to do a very similar thing for PC prime. And the critical pressure is 35.407 atmospheres. So now I'm going to find the reduced temperature and pressure. So the temperature is 305 Kelvin. The pseudocritical temperature is 211.827 Kelvin. And so TR is 1.44. PR is going to be 2.26 over 35.407, 0.0638. Next, we're going to go to the charts. And if you do that, we need to work on reading those charts. So in this particular case, what we have is we have a temperature of 1.44. So each of these curves represents a different value of T sub r. So 1.44, I have a 1.4 and a 1.5. 1.44 is kind of in between these. And I'm kind of visually interpolating where I think this curve should go, okay? So there's my TR is 1.44, okay? PR is 0.0638. So reduced pressure is across the bottom, and I'm just going to read this. Now this is a logarithmic scale. Now on a logarithmic scale, you'll notice that the numbers, they count in what's called decades, so 0.1, 0.2, 0.3, 0.4, 0.5. If you were to continue with this, 0.6, 0.7, 0.8, 0.9, and then it goes to 1. But the next number is not 1.1, the next number is 2, 3, 4, 5, 6, 7, 8, 9, 10, and now then again, instead of going 11, counts the next decade, 10, 20, 30. So this is a logarithmic scale. It requires a little bit of practice reading it. Our value is 0.06 for PR. And my scale stops here at 0.1, so 0.06 is going to be somewhere over here. Can I read this chart? Well, if you look at this and see where all of these extend, they all are coming in, and they look to me like Z is very close to 1. It's coming in to where they all scrunch into 1. Now why would this be? Because look how low PR is. We said that for very low pressures, the gas is going to be very close to being an ideal gas. So if one were to do this, N is going to be PV over ZRT. We have 2.26 atmospheres. The volume is 1450 meters cubed per hour. Z is approximately 1. The temperature is 305 Kelvin. And R, I'm going to use 8.314 meters cubed pascals per mole Kelvin. Okay, so I'm in pretty good shape here, but I've got pascals and atmospheres, so those don't quite work. So I'm going to take all this and multiply it by 101.325 pascals per 1 atmosphere. And this is therefore approximately 132 kilomoles per hour.